All right. Hi, everyone. Good morning. My name is Dillan Newbold. I'm an MD PhD student at Washington University in St. Louis, and I work with Nico Dosenbach. Our lab is interested in understanding how functional network organization develops in the human brain and how the brain changes in response to changing situations. And so, just a second. Slide advancer isn't working. Oh, all right. And so I'm going to start out very basic. I promise I'll go through this very quickly because I'm sure almost all of you know this already. In fact, out of curiosity, how many people here have seen this figure at some point in their careers? This is from Biswall, published in 1995. All right, so that's like a lot of you, but it looks like some haven't. So I'll explain it very quickly. So what Biswall showed, again, my slide advances. Okay. What Biswall showed is that brain regions show constant fluctuations in intrinsic activity. And if you look at functionally related regions, these fluctuations are tightly synchronized. Biswall termed this effect functional connectivity, and he quantified it using a correlation across time. So on the left here,
please do not point your in the computer. You should point here.
Okay, that
because
sounds great.
Yeah.
So on the left here, the colored voxels indicate regions that show functional connectivity with this seed region of interest in the left somatomotor cortex. So this is basically the Biswall figure. And you can see high functional connectivity in the supplementary motor area, as well as the right hemisphere. And this has been a tremendously useful effect. This is the basis of thousands of papers, many thousands of papers. But despite that, it's still sort of mysterious. We don't really know why this happens. Why do these distant brain regions show this tightly coupled activity? And so I think that today I can help constrain your thinking on why that happens. Because in my lab, we have discovered a condition in which this effect, this functional connectivity between the left and right somatomotor cortex disappears. Okay, so this is how we did that. We had 3 right-handed participants wear a cast covering their entire right arm and hand for 2 weeks. And then we sent them out into the world to perform their normal behaviors, but without their right hand. And then these devices you see on their wrists, these little red devices, are accelerometers. Those let us monitor their behavior throughout the day, throughout the experiment. The accelerometers showed that casting caused significant disuse of the right upper extremity, as you might expect. What I'm plotting here on the y-axis is the percentage of seconds during any given day when subjects moved their right arm. These measurements are binned by week, and the colorful bins represent the casting periods for each participant. And this will be sort of a consistent color code throughout the talk, so the colors correspond to the cast colors for each participant. We saw significant disuse of the dominant upper extremity. There was also slightly increased use of the non-dominant upper extremity, which was not casted. And this severe disuse had functional consequences. All of our participants lost about 40 pounds of grip strength when we took the cast off. And unfortunately, this returned to baseline fairly quickly. And then we wanted to know if this disuse also had consequences for brain function. And so we collected 30 minutes of resting state fMRI data every day for 6 to 10 weeks. And so that is over 100 hours of resting state data between our 3 participants. This really dense sampling time course is sort of our lab's niche, I guess. And when we do it in an experiment like this, it allows us to track a daily time course of functional connectivity changes. And we are able to test hypotheses individually in each participant, which is why we have 3 of them. So before I showed you this figure, and on the left, this was a seed map. So again, this is a functional connectivity seed map from the left somatomotor cortex. And this is one session acquired for one subject during the baseline period before casting. And then on the right, this session was acquired near the end of the casting period. But since we acquired daily data, I don't just need to give you a side-by-side comparison like this. I can show you a daily time course of functional connectivity changes. So we defined regions of interest in the left and right somatomotor cortex individually for each participant using task-based functional MRI. And then this is a daily time course of functional connectivity for our first participant, who, by the way, was my advisor, Nico Dosenbach. He actually casted himself so we could, in part, so we could make sure that this was a safe thing to do to people. And so each dot represents one 30-minute session. And you can see consistently high functional connectivity between these regions at baseline, which progressively declines throughout the casting period and returns to baseline after we take the cast off. And the black lines here come from a general linear model, which fits the mean and slope with time for each period of the experiment, before, during, and after casting. And the delta R value I plot here is a comparison between the mean functional connectivity before casting with the sort of modeled end of casting based on the general linear model. So that's a way to let us use a lot of data to make that comparison. And when we saw this delta R of 0.32, and we were shocked by that, because there have been several studies that try to do something sort of like this before, change functional connectivity with some sort of behavioral training paradigm, and the largest effect size that I've seen, at least, is around 0.1 or smaller. And so since we saw that, we decided to repeat this in a second experiment, and we were absolutely blown away. In this participant, we found a delta R of 0.99. This is by far the biggest change in functional connectivity I've ever seen in the literature. This is not in the literature yet. Hopefully it will be soon. And then we repeated it one more time, and we saw a similarly large change in connectivity. You can see there are also other interesting differences in the time courses between these participants. And so clearly there is a strong effect between, strong relationship between functional connectivity and a person's recent behavioral history. And so it seems as if brain networks require consistent use in order to maintain their normal functional organization. And I'd love to tell you more about these changes in functional connectivity, and anybody who's interested should come to my poster this afternoon. I'll tell you all about it. We have a few other interesting effects. But right now I want to tell you about something a little different. We wanted to understand why functional connectivity is changing here. Go a little deeper than just measuring a correlation between these ROIs. So to do that, we started by just plotting out the full time course from both of these regions of interest. So here I'm showing 30 minutes of bold fluctuations. In blue is the left somatomotor cortex, and red is the right. And we casted the right arm, so it's this left somatomotor cortex that was disused during the casting period. If I shrink this down, then we can show all of the sessions, almost all the sessions for this participant. And the first time we ever looked at this, we almost immediately noticed there's something very interesting happening during the casting period. If I zoom in on a part there, what we saw are these large, spontaneous pulses of activity in the disused motor cortex. We can detect these pulses using a threshold-based spike detection algorithm, and then that allows us to count how many of them are happening in each session. And so in every participant, there were many of these during the casting period, and some after casting, and virtually no similar events before casting. And so we think that this is a very specific effect. We're very interested in it. Once we found all these events, we were able to average them together and create a mean pulse time course, which looks like this, playing out as a GIF. If you look at this time course in the left motor cortex, it looks a lot like a hemodynamic response function to a very short burst of neural activity. And then this doesn't only happen in the left motor cortex, interestingly. It also involves the supplementary motor area, the motor cerebellum related to the casted extremity, and there's a slight deactivation in the right somatomotor cortex. And so we aren't exactly sure what these are yet. We have some ideas. One potentially related observation in animal data is that various paradigms involving disuse, for example, monocular deprivation or deafferentation, lead to a rapid disinhibition of the disused cortex. There's lots of great literature on that dating back decades. And so that is potentially related. There might be some other possibilities for what's contributing to this. I'm very interested in hearing other ideas about what these could be. And so if you have any ideas about that, or if you're interested in learning more about this work, please come to my poster. So this afternoon, this is what it looks like. This is what I look like. So hopefully you can find us. I'll be there from 12:45 to 1:45. My poster number is W691. I want to thank all 3 of the participants who did so much to make this experiment possible. They all came in every single day to scan, and they also wore this gigantic cast on their arm for 2 weeks. I also want to thank all the people in the Dosenbach lab and elsewhere at Washington University for helping me to analyze and interpret this data. And I want to thank all of you for listening. I'll take any questions.